Hello, I'm Todd Thiedel, and this is part 4 of vectors. This time we're going to be learning about vector components, how to find them, and what they're used for. Okay, so components of vectors. So the resultant is the result of adding and combining vector quantities. This means that the resultant has the same effect as if the vectors that were added. So two vectors are added. It's sort of like the airplane and the wind are two vectors, and the result is what happens when they're both acting on the plane. Components are either horizontal or vertical of the vector, and the components are perpendicular to each other. That makes it really handy. It is like we are unadding. So we're going to take a vector and we're going to unadd it to its components. This has a special name. This is called resolving the vectors. So watch for those instructions when you come across. Okay, so vector resolution, there are two common components. The x component, which is along the x-axis, and the y component, which is along the y-axis. Could also be parallel to either one of those axes. To find the components of this vector v that's directed with an angle theta, the y component, or called the vertical component, is calculated by multiplying the magnitude of the given vector times the sine of the angle within this right triangle. The x component, which is referred to as the horizontal component, is found by multiplying the magnitude of the given vector to the angle within the triangle also. So very convenient, fairly easy to find. We'll do some examples to find that. So here's one. We're going to find the components of the vector that is 200 meters directed along 110 degrees. So as all vectors, I start out by sketching a graph, or just sketching it. It doesn't have to be to scale, but just so sort of give a picture of what's happening. So I have this 200 meter vector going along that 110 degree angle. First thing I do is I draw out the vectors. So the Vx is along the horizontal axis, and the vertical Vy is on the other side, forming this right triangle, because remember the two components are perpendicular to each other. So before I can resolve this, then I must figure out what that angle is inside. Because this is the 90 degree angle, I take out the 90 degree angle from 110, and so I get a 20 degree angle inside that right triangle. So to calculate the x component, I simply take the magnitude of 200 and multiply it by the cosine of the angle inside the triangle. So putting that in, that's 200 times the cosine of 20 degrees. I'll pause here while you calculate that, or you can pause the video. Multiplying that out, I get 188 meters. Now, if it came out to some strange number, not 188, you're probably in radians. Just always check to make sure you're in radians, especially if you're coming from math class where you may be using radians. So make sure we're in degrees when we're calculating this. Okay, so calculate the vertical component, the y component, the one going down. I take the magnitude of 200, multiply by the sine of the angle. So it's 200 times the sine of 20. That calculates out to 68 meters. So I know now that the two components, the horizontal is 188 meters and the vertical is 68. Okay, fairly straightforward, not a problem. Just as you know that the x component is uses the cosine because it's adjacent to that angle, and the vertical the y component is opposite the angle, so we use the sine. That should help you remember which is which. Okay, so let's do an application problem. So we have an airplane that flies at 650 kilometers per hour at 35 degrees south of west. And we're going to find the components of the plane. So here's my airplane. I'm going to draw out a vector to represent its velocity, 650 kilometers, directed at 35 degrees south of the west reference. I'm going to then draw in the two vectors. So I have the horizontal. We can actually refer to this as the west component because we have a reference for that. And we can call this the south component. So by calculating, the x component is V 650 times the cosine of the inside angle 35. And that calculates to 532 kilometers per hour. Calculating the vertical component, or the southerly component, now I use the sine because it's opposite the 35 degree angle. Plug in 650 times the sine of 35. Calculate 373 kilometers per hour. So that means that the plane is flying west at 532 kilometers per hour and south at 373 kilometers per hour. The resultant, of course, is the 650 kilometers per hour along the 35 degree angle south of west. Pretty straightforward, yes? Okay, so now an application for this. Adding vectors, we're now going to add vectors by using components. This is another way of adding vectors. We've already learned how to add vectors graphically. That's by drawing them to scale. We've then learned about adding vectors analytically, the ones that are at right angles to each other. So now we're going to actually use components. So we're going to add the x components together, and we're going to add the y components together, and then we're going to add those two results together. You'll see how that works in this example. Okay, here's an example. We have 350 meters per second at 70 degrees, plus 75 meters per second at 135 degrees. So I'm going to sketch these out. 70 degrees is from due north. Pause it when you need to if you want to work along with me. So 70 degrees is from 0, 350 degrees. At the end of that, I'm going to put 75 meters per second along the 135 degrees. That is also from 0. Then I am going to resolve these into components. There's my x component on my first one, and then my y component on my first one. Because that's a 90-degree angle, I figured the 20-degree angle on the inside of the triangle. Remember, you have to have the angle on the inside of the triangle in order to calculate the components. For the red one, then put the x vector, the x component up there, and the y component on the opposite side, forming this right triangle. Then I need this angle on the inside. I take out the 90-degree angle, and then I have a 45-degree angle on the inside. Okay, so those are the components. So here's what I'm going to be doing. I'm going to find the value of this x component. I'm going to add to it the value of that x component, because that will be the x component of the resultant, which would go from the open tail to the open head. I'm going to use that, and then I'm going to find this component, and I'm going to subtract out this one because they're in opposite direction, and that would be the y component of the resultant. Okay, you see how this works. So first I calculate this x component, 350 times the cosine of 20 degrees, 329 meters per second. We calculate the y component, and that's 350 times the sine of 20 degrees. It comes out to 120. All right, I'm going to go ahead and calculate the x component of the red one, 75 times the cosine of 45, which is 53. And then the y component will be 75 times the sine of 45, which happens to be the same value as the cosine of 45. And that comes out to 53 also. Okay, so now I'm going to take the x components, I'm going to add them together, and that's going to be the x component of my resultant. I'm going to take the y's, because one y goes up and one y goes down, I am going to subtract those values. So it's 120 minus 53. I'm then going to draw in my resultant, and notice that that vector would fit right between the open tail and the open head. Now I have simply a right triangle to find the hypotenuse. I'm going to use Pythagorean theorem. So it's 382 squared plus 67 squared. Calculate that out. And that comes out to 387, which is logical because it's larger than that. It's got to be bigger than the 350. I then have to find the angle because we're finding the resultant. So put theta on the inside of my right triangle, and now I'm going to use the inverse tangent function, 67 over 382. Calculate that in degrees, and that comes out to about 10 degrees, and that's north of east. So the resultant of those two vectors is 387 meters per second at 10 degrees north of east. I realize how busy this all is because there's a lot of little things in there, but the concept is if you combine the x components, that will equal the resultant's x component, and combine the y components, that will be the y component, and then you use simple Pythagoreans and inverse tangent in order to calculate that. Pretty slick, huh? It will get more complicated if you have more vectors, and sometimes they cross over each other and it gets a little confusing. But this is a pretty surefire way of doing that. Okay, so on your practice, there's a section 4. Do that in your notebook. Okay, well, thanks for watching. Just let me know if you have any questions. You can contact me by the usual ways. Okay, thanks.